Alright, section 9.5 is graphing and writing equations of hyperbolas. And you've actually done hyperbolas. I'm not sure if you remember, but let me just give you a visual. You did hyperbolas in chapter 8, it would have been. This is an example of the hyperbolas that you did. However, you are going to be doing different hyperbolas now. So the hyperbolas that you're going to be doing are going to be horizontal or vertical, just like the parabolas and ellipses that you did. Those were also horizontal and vertical. So for example, you might have, let me just give you an example. You might have hyperbolas that do this and this, which obviously are horizontal hyperbolas. You might also have hyperbolas that do this and this, and those are vertical hyperbolas. A couple things to note about hyperbolas is you're going to have those cool asymptotes that the hyperbola branches approach, and we're only going to look, again, geometrically speaking at hyperbolas, so it's going to be the horizontal or the vertical and not the ones that you did in chapter 8. Alright, here we go with good old important characteristics. So when you're dealing with a hyperbola, remind yourself that I'm going to ask you on the exam to list the important characteristics. So that's going to involve, and I'm not going to remind you, that's going to involve the foci, vertices, and the center of the hyperbola. And in addition to that, although I didn't define it because you already know what they are, is you're going to be asked to list asymptotes. So add that to your list. So I'd pause the video and jot down important characteristics about a hyperbola are foci, vertices, the center, and the asymptotes. Okay, so now a hyperbola, and I have a visual here, the definition of a hyperbola, geometrically speaking, is the set of all points P such that the difference of the distances between P and two fixed points called the foci is constant. Now if you remember an ellipse, I could pick any point on an ellipse and calculate the distance from that point on the ellipse to both the foci, and the sum of those would be fixed no matter what point on the ellipse I chose. Here with a hyperbola, instead of the sum, it's the difference. So the difference of those distances will be fixed. So, for example, I'm just going to pick any old random point here on this hyperbola. Actually, let me blow it up for just a second. So looking at this lovely hyperbola, I'm going to pick a point, right here. If I calculated the distance to this focus point and the distance to that focus point, that difference is going to be the same as if I pick a different point on the hyperbola. So let's say I pick, this point right here. That distance minus that distance, actually the other way around, always take the longer minus the shorter, will be, so the difference in the orange lengths will be the same as the difference in the red lengths. I can pick a different point on the hyperbola, let's say this one. I can calculate the distance to the two focus points, and the difference between the red, or excuse me, the blue lines will be the same as the difference between the red and the difference between the orange lines. So I think you get the idea here. So that is the definition of a hyperbola. Now foci, you're already fairly familiar with this. So foci are the two fixed points in a hyperbola. I'll just highlight that they're inside the hyperbola. So if you have your hyperbola branches that maybe look like this, your foci are going to be inside those hyperbola branches. The vertices are the points of the intersection of a hyperbola and the line through the foci. Okay, so the vertices of these hyperbola branches are right here in red. So those are vertices, the point of intersection through the line that contains that foci, right? Transverse axis won't be something you have to write out, but that is the line segment that connects the vertices to the hyperbola. So your transverse axis in this case happens to be my x-axis. And then of course the center is the midpoint of the transverse axis. So let me select a different color here. So the midpoint here happens to be my origin. So halfway in between my vertices, halfway in between my foci, very similar idea to that of an ellipse. And these are your important characteristics for a hyperbola. The one other thing I would note is asymptotes, and you know what an asymptote is, but more importantly, you're going to be finding those asymptotes. So when you do an asymptote with a hyperbola, what you're going to be doing actually is you're going to be finding the vertices, which I have in red, and you're going to be finding some other points, and they're not called covertices, but they're going to make like a little, well, a little rectangular box, I guess, is what that's going to amount to. And then your asymptotes are going to fit from corner to corner. So if I went from corner to corner on this box, that will create my asymptotes. And your asymptotes always go through the center. Always, always, always. So wherever your center is a fixed point for sure that will go through both of your asymptotes. And you'll see examples of that soon. All right, last on this intro video is all the equations that you need to know. So note that this is standard form equation of a hyperbola with the center at the origin. Okay, so keeping in mind that your hyperbola branches are going to be centered at the origin. So if you have a horizontal hyperbola, I'm just going to squeeze one in right here, your hyperbola branches will be opening in the x direction. If you have a vertical parabola, excuse me, I keep saying parabola, if you have a vertical hyperbola, your branches will be opening in the y direction, hence being vertical of one another. So now, note the equations look real similar to an ellipse, and that can be tricky, but first I want you to note, instead of adding the x squared and the y squared pieces, you're subtracting them with hyperbolas, so that's the one big difference. They do both equal 1, like that of an ellipse. Also notice there's an a squared and a b squared, like an ellipse. However, the a squared and the b squared don't switch from the horizontal to the vertical. So a is not larger than b. Okay, so do not, in fact, maybe write that down. With an ellipse, the a squared, it has to be bigger than b squared. With a hyperbola, nobody cares what a squared and b squared are. They can be, b squared can be larger than a squared for all that matters. However, note that the x and the y squared switched. So if x squared comes first, and then it's minus y squared, you have a horizontal hyperbola. If the y squared comes first, and then you subtract the x squared, you have a vertical hyperbola. And that makes sense because the order of subtraction is obviously important, so if I switch the x and y around, that's going to make a difference in my horizontal versus vertical hyperbola. So if I have a horizontal hyperbola, I just want you to note that your vertices are on the x-axis if it's centered at the origin, right? So my vertices over here are at a plus or minus a0, so they're on the x-axis. If it's vertical, my vertices are on the y-axis if it's centered at the origin, so then my vertices are at 0 plus or minus a. So on the x-axis horizontally, on the y-axis vertically. I'm going to come back to the asymptotes. Notice that your foci are found by this lovely equation that should look familiar. C squared equals a squared plus b squared. So an ellipse is a squared minus b squared, but a hyperbola is a squared plus b squared. So another thing you're going to want to note, you know, there's little differences about hyperbolas and ellipses. Obviously, the shapes are very different. And then last but not least, your asymptote. If you have, I'm just going to draw just a sketch of a hyperbola here. If you have a, we'll say, horizontal hyperbola that's centered at the origin, your asymptotes for sure are going to be, if you think about your asymptotes here, I'll use a different color actually for my asymptotes, are going to be here and here, and you can probably see that. So it's going to for sure go through 0, 0, and I said that already. So notice that your asymptotes here don't have a y-intercept. It's not like plus anything, it's just plus 0. So no y-intercept because it's going through 0. And if you look at this asymptote, you're going to go up a certain amount of points and over to the right a certain amount of points, and you're going to get kind of to the corner of like this rectangular region right here. This distance, well, this distance actually is going to be a, right? Because you know that you have vertices here at a and negative a. based off the definition here. So if this is A, I know that my rise is going to be a certain number, and my run is for sure going to be A, and that's where this comes from. My rise happens to be B. So how cool is that? The A and the B you should be able to pick out from your formula. Another really slick way of remembering this is think about slope. Slope is change in y over change in x. Well, the number underneath y is b squared, and the change in that would be the square root, or just b. And the change in x, the number under that, is a squared, and the square root of a squared is a. So it's always the number under y over the number over x. So now if you envision, of course, a vertical hyperbola, still centered at the origin, right? Your vertices now are on the y-axis, and if I kind of envision my asymptotes there, the slope of this asymptote is going to be rise over run. Well, my rise now is going to be my A value, and my run is going to be the B value. So again, change in Y, so A comes first over change in X. So they just flip-flop from here to here. Now, I don't know that you necessarily even have to reference this equation, because you're going to be able to really just look a lot of times at the graph and figure out those asymptotes. And I'll walk through, obviously, some examples in your example video.